Let us look at the second order cone program, or SOCP, which is a new class of optimization problems, more general than QP or QCQP. So the general form for the SOCP is of this form: minimization of over X, F transpose X, norm of AI X minus BI less than equal to Ci transpose X plus Di. This is for some I from 1 to m, and we may have, of course, some equality constraints, and then there are implicit constraints saying that Ci transpose X plus Di greater than equal to 0. So these are implicit. We may not necessarily specify them explicitly. So the key thing to notice here is this constraint. This is essentially, if you express it in another way, you can see that this is of the form AIX minus B norm minus Ci transpose X minus Di less than equal to 0. Note that this part is affine and this is convex. Norm is convex. So convex plus affine less than equal to 0. This is fine because we allow convex less than equal to 0 kind of constraints. So this is a convex optimization problem. SOCP is a good example where the convexity actually depends on the way it is formulated. For instance, you will find yourself in trouble if you actually square this. So for instance, let's consider a simple example. Let's say that you have a constraint of the form norm of X minus T less than equal to 0 in X comma T. This is clearly convex because norm is convex minus T is affine. So convex plus affine less than equal to 0, this is fine. However, if you square this, then you will get a constraint of the form norm square of X less than equal to T square, or norm square of X minus T square less than equal to 0. Here, norm square of X is convex, but minus T square is concave, right? So we have a convex plus concave less than equal to 0, and therefore this side is not convex. Remember that in our standard form, we were only allowing convex function less than equal to 0 inequality constraints. So that would not be the case here. In fact, this is not convex. You can verify by finding the Hessian with respect to X and T. So you will find that if you find the Hessian will have one negative eigenvalue and all others positive. So this is actually not neither convex nor concave. So therefore, if you formulate it in this way, it is not convex. But if you formulate it in this way, it is convex. And this is an important part of, or an important example of SOCP, which shows that if you formulate the SOCP in a different way, it may look to be non-convex, but actually it is convex if you formulate it like this. So in general, I have not talked about it so far, but in general, in terms of algorithms, we already discussed that LP or algorithms for LP are the fastest. LP is a special kind of problem, and a generalized version of LP is the QP. So if you remember, in the QP, we were using the objective function of half X transpose Px plus Q transpose X. So if we just take P equal to 0, we would get the LP. So QP is a generalization of LP. Every LP can be written as a QP with P equal to 0. Yet another generalization is QCQP, because in the QCQP you could take the constraints as linear and you would get the QP, and linear is a special case of quadratic. And even more generalization of that is the SOCP. So SOCP is more general than QCQP. In fact, every QCQP can actually be expressed as a SOCP. So let's see this. Let's try to express a QCQP as an SOCP. So let's say that we have half X transpose P naught X plus Q naught transpose X subject to half x transpose pi x plus qi transpose x plus ri less than equal to 0. So this is a QCQP. We have already seen this. Let's try to express it as a SOCP. Note that the converse is not true. So it is not necessary that you can always express a SOCP as a QCQP. We have already seen this here. If you have a constraint of the form norm of x less than equal to t, squaring it will get you nowhere. In fact, this would not be a quadratic constraint, a convex quadratic constraint. Right? So this would not be a convex quadratic constraint, and therefore squaring it, you will not be able to get a QCQP back. So SOCP is really more general than a QCQP. So let's see this. Remember that we are considering convex case. So P0 and Pi are all positive semi-definite. For a positive semi-definite matrix, this one can actually be written. So please verify this. So this can be written as square root of Pi times x. Remember what is square root of Pi? Pi is equal to square root of Pi times square root of Pi. This is a symmetric square root of a positive semi-definite matrix. So this can be written as square root of Pi times x plus square root of Pi inverse times Qi. Now I'm assuming here that these are all positive definite. So this square minus Qi Pi inverse Qi plus Ri. So this thing can be written like this. So therefore the constraint can be written as, so this means that the constraint can be written as, so you just take square root on both sides, square root Pi x plus Pi inverse Qi norm less than equal to square root of Qi transpose Pi inverse Qi minus Ri. Note that we would therefore require this to be greater than equal to 0. So actually this is generally required for this convex quadratic constraint to be feasible. This is generally required that this quantity is greater than equal to 0. So now we have been able to write this QCQP as minimization of P0 x plus P0 inverse Q naught subject to constraint of the form square root Pi x plus square root Pi inverse Qi less than equal to Qi transpose Pi inverse Qi minus Ri. So we have already been able to write it with a objective which is norm and therefore convex, and the constraint which is of the form norm less than equal to a constant. Norm less than equal to a constant is fine because QCQP we had said that it is of the form norm or of an affine less than equal to affine. So constant is a special case of an affine. And further we can again use the epigraph trick to write it as minimize over t subject to constraint square root P0 x plus P0 inverse Q0 less than equal to t and square root Pi x plus square root Pi inverse Qi less than equal to this constant which is Qi transpose Pi inverse Qi minus Ri. So this is finally a required SOCP. Note that this is exactly the second order cone constraint. Right, so that is the second order cone constraint because we have an affine norm of an affine less than equal to t. Right, so this is a generalized version of second order cone constraint, and this is simply a norm ball constraint. So that is what an SOCP entails. So if you are required to express any problem as an SOCP, remember that you need to express the constraints which should be of the form affine and then norm outside less than equal to another affine. There should not be a square here. So let me emphasize that there should not be a square here, and you cannot take square root. Sometimes people take square root of the where the variable contains x. So that is also not allowed. Here you have to have a norm less than equal to affine. So that is all we have for our discussion on SOCP. We will look at various applications of SOCP later on, particularly in the context of robust optimization.